What is going on, everybody, and welcome to part 4 of our Deep Learning with Neural Networks, TensorFlow, and Python tutorial. In the last tutorial, what we did was we basically built up the computation graph for our TensorFlow model, and also basically we built up the neural network model. So those two are very synonymous as far as what they are. So your model, for your machine learning model, is very similar to setting up the computation graph. And then what we have left to do now is specify how we want to run data through that model in the session. Okay, and what we want to kind of do with that model in the session. So to do that, let's go ahead and we're going to create a new function. That's going to be train neural network. This is going to take X, which is just your input data, and we're going to say the prediction is equal to the neural network model X. So what's happening here? You're taking input data, you're passing it through your neural network model, which shoves it all through the layers and returns an output. Recall that output is that one hot array, right? That thing where it's like 0, 0, 1, 0, 0, 0, and so on. That's what it returns. So your prediction is that. And then what we're going to do is we're going to say the cost, right? This is our cost function, is equal to tf.reduce_mean, and we're going to do that on the tf.nn softmax underscore cross underscore entropy with logits against the prediction and y. So in this case, what we're doing is we're using cross entropy with logits as our cost function, and that's going to calculate basically the difference, let's say, of the prediction that we got to the known label that we have. And both of these are that one hot format. That's why we basically, this one hot equals true. That's why we have that, and that's why our output layer is of that shape and everything. So, but of course, if you're not using one hot, that's totally fine. You can have your output be whatever shape. Your output basically will just always be the shape of your testing sets labels, right? So just keep that in mind. Training and testing sets labels. Hopefully you don't have those different because you're going to be screwed. Anyway, so now we have the cost function. We know what the cost is. What do we do with that cost? Well, we want to minimize that cost. We want to minimize the difference of prediction and y, right? We want that to be as small as possible. Ideally, no difference and 0. But that rarely happens. So anyway, we're going to have an optimizer, and the optimizer is going to be tf.train.atom optimizer, and this is synonymous with stochastic gradient descent, eta grad, and so on. And this would be, so using the atom optimizer, what do we want to do? Well, we want to minimize. What do we want to minimize? Cost. Done. Optionally, the atom optimizer does have a parameter that is learning rate, but learning rate default equals 0.001, which is a fine enough learning rate, so I see no reason to modify that. Okay, so we've got those values, and we have our cost function defined. But again, what is anything actually happening in this cost function? I mean, just look at it. Like, nothing is happening in the cost function. How about in the optimizer? Is anything actually happening here? We're minimizing cost, but are we actually running anything? Are we running it through layers or telling the optimizer how to minimize cost? I don't see how, but okay. Now, we're going to start with how many epochs do we want? And this can be any value. We'll start with 10 just so it goes a little fast. If you are following along on a really, really slow computer, probably do like a really low number there, or don't do this at all. I don't know what you're doing with neural networks on a really slow computer, but it'll run. It just might take a while. So yeah. Anyway, how many epochs? 10. Like if you're on a netbook, I wonder how slow this would be. Anyway, with tf.session as ses, what do we want to do? Well, first we need to initialize our variables, so we'll do ses.run tf.initialize all variables. I feel like they need to just have like a tf.init or something rather than like init vars or something. Anyway, that's a long thing to type out, I'm just saying. Okay, so that initializes our variables, and And that actually begins now. The session has started running, right? The session has begun. We're done defining our computation graph at this point. So we're going to run through these epochs. And again, the epochs is just cycles, right, of feed forward plus your back prop, right? So your forward data and then back prop fixing all the weights. Okay, those are your epochs. So once you've done that, what we're going to say is we're going to say for, for epoch in how many epochs do we want? We're going to start by saying the epoch loss is currently at 0. And we're going to kind of just like calculate the loss as we go. We could say epoch cost or something too. But we're going to calculate that as we go. And then we're going to say for underscore in range. Underscore just is like shorthand for variable we don't care about, by the way. In range of the int value of mnist.train.num examples divided by the batch size. Okay, so this is just basically we have the total number of samples. We're dividing by our batch size, and that tells us how many times we need to cycle based on that dynamic batch size that we set way up here. So we do that, and we're just going to iterate through. As we iterate through, we're going to say x and y, so data labels equals mnist.train.next batch size. So what this does for you magically is basically kind of chunks through the data set for you. Now, when you do this in the real world, you would have to like build your own little function that does this for you, right? It just so happens that they've got this pre-built to do batch sizes for us, but this kind of makes it look a lot easier than it really is. But I suppose it's not that hard to make something that does this. But there are a lot of like little helper functions like this in TensorFlow. It's actually quite nice. I was pretty surprised given what I had heard about TensorFlow versus my actual reality of using it. Anyway, variable we don't care about, C, equals ses.run. C is cost, by the way. What are we going to run in this session? We're going to run the optimizer and the cost, right? Recall, optimizer, this, cost, this, right? They are just simply definitions in our graph. We are going to run the optimizer with cost, and then using their feed dict, the data is, feed dict, sorry, my microphone's in the way of my keyboard. Feed dict equals, and we're going to say x, y, y. Done. So we run through the data, and we're running that. We're optimizing the cost with x's and y's, and we're passing the x's and y's, right? We see x's and y's. How are we optimizing that cost, you ask? Right? We are doing that by modifying the weights, and yes, the weights are, or by modifying these weights, and yes, those weights are being passed through these layers, but somehow, magically, TensorFlow knows that, and biases, that it gets to modify those. So, incredible. It's just, it's a little high level. I mean, that was a kind of like one of the most confusing things for me as I was coming into TensorFlow. But anyway, epoch loss plus equals whatever C is. Okay. And then for each epoch, we're obviously resetting the epoch loss. But we kind of want to track that each time. And then after that for loop, what we can do is we can just print. We can do some beautiful formatting here. Epoch. Completed out of, what was it? How many epochs? HM epochs. And then we can say loss. No, epoch loss. Perfect. Done. Okay, now that will give us the answers or the loss function and tell us where we are. Obviously, if you don't print something out, you'll have no idea. Like, how much longer do I have to wait? So it's kind of useful. Do that. You could also do something in the batches. Like if you had like a huge data set and your batch sizes were huge, you could do that there too, just so you kind of, and then you could kind of generate like a percentage complete kind of thing. But for this data set, that won't be necessary. Anyway, now outside of the for loop for the epoch and how many epochs, I do like the little lines that are there, I will say. Idle is still the best. Correct equals tf.equal. So we're just kind of asserting tf.argmax prediction 1, tf.argmax y1. So all this is doing, tf.argmax is going to return the index of the maximum value in these arrays. And we're hoping that those index values are the same, right? They're both 1-hots and all that. So we're expecting that this is going to tell us whether or not these are basically identical. So that's that. Now, we can compute accuracy as being equal to tf.reduce mean tf.cast, which just changes the variable to a type. So we're casting correct to a float. Because before it's just, I don't even know what the default type would be. I mean, tensor of some kind, but I don't. Anyway, I don't know. Anyway, it's a float now. And then we can just say printy accuracy, comma, accuracy dot eval, and we are going to evaluate x colon mnist dot test dot images, and then y colon mnist test dot labels. Okay, so after we've trained, because like basically this is just training the network, or at least this. So up to this point, we're just training. We're dealing with training data, right? mnist.train. We're dealing all with training and train here. We're dealing with the training data. And then once we have optimized those weights, we come down here and run them through our model. And we're saying that to know what's correct or not, we compare the prediction to the actual label. Accuracy is just whatever the float is of that correctness. And then we're going to evaluate all of those accuracies of basically the test images to their test labels. Again, we're not telling it like feed this data like through the model or anything. Like it just does it. Great. I mean, I don't know. Some of this stuff is maybe too high level, I think, for my review of TensorFlow. But at the same time, it's pretty cool. Like this is and I have some white space. I mean, it's decent. But this is 66 lines of code. That's incredible. And by the way, yeah, we're done. So now what we do, everyone's like, run it. We're just going to train network X. Right? We pass X. That's it. Done. So now let's test this bad boy. So we come over here, and that's just from before. We'll just Yep. Python 3 deepnet.py. Please don't give me an error. Oh, God. I knew we were going to do this. Okay, so layer 1, we're missing one required positional argument. Add matmul. What do you mean? What am I missing here? All right. So I paused it while I was trying to figure this out, and I figured it out. So I should have paid a little bit more attention. But anyway, add missing one required positional argument, a y. So when you add, you have an x and a y, right? You add and then xy. And instead what I had done, which I probably actually could have gotten away with after we showed the whole multiplication and all that, but I'm doing tf.add this plus this, right? Which, kind of made sense if it wasn't within a tf.add. So actually, rather than this plus, you have a comma, okay? And then another comma here, and this one is a matmul without the add. So that should tell you right there that you actually can get away without the add. So you can do tf.add or just a straight up plus. You actually don't need the add. Interesting. Okay, so we'll save that. Let's try again. See what happens this time. Local variable y. What are you talking about? So this time it's telling us y was referenced before the assignment. And that would be the y in the softmax function. So up here. I don't know about y'all, but I honestly already see a y being defined. But I wonder maybe if what's happening is here, that it's getting angry. So why don't we say epic x, epic y. I wonder if like this is screwing that up, because again it doesn't work like Python works, so you can't necessarily use bad code that you write in Python. So epic x, and then let's try this to be epic y. Sorry for the errors, but I'll probably end up leaving them in because I think they're fairly useful, because it's easy to make stupid mistakes like this. The first one was a stupid mistake. I'm guessing this will fix this one, but we'll see. I should stop surmising and just find out. Okay. Okay, so here we have an invalid argument, but it's not telling me like where. That would be really useful. So clearly we got an empty, something was empty that it didn't want to be empty. Ah, that's it. Okay, so as painful as that is, or that was, recall, these are all basically needing to be arrays here. So here, all these biases, here, 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 and this one I actually did correctly, interestingly enough. Anyway, that one was a little harder to get to, but anyway, yeah, you get that first trace back, and then another exception occurs, and that's where I got to read here. I was like reading this, and I was like, what's wrong with this line? But that's it. This needed to be, square brackets. Okay, so let's save that again. Oops, what just happened? Okay. Save that again, and let's try again. Ah, yes, we left this commented out. At least we know we made it to that point. I shall try again. This is getting brutal. Clearly, I'm just having a bad day for epic in range of how many epics. All right. This is going to be the death of me. Please don't give me an error. I'll have to jump out my window. Luckily, I'm on the first story. Here we go. That's a big loss, but that's probably decent. Whew. Massive improvement. That's what we need to see. We need to see improvement here, guys. Let's see. I wish I knew how to make this bigger. Someone knows how to make this text and this bigger, it'd be great. Hopefully you guys are running though. And I imagine the batch thing, or the square brackets, you guys for sure made that mistake. I'm not sure if everybody made the range mistake though. That was pretty dumb. Anyway, so you can see this is pretty slow. Now, the good news is once you've trained a model, right, you don't have to keep doing it. So if you've been following along in the series, you've seen that like with scikit-learn, you can pickle the model and you don't have to retrain it again. Anyway, so we're done. The accuracy is 94.85%. So perfect accuracy would be a 1.0. So we got almost 95%. And on the MNIST dataset, that's actually considered like laughable, but that's only considered laughable because this isn't quite the best model to be using on the MNIST dataset. Mostly because, like, consider again that all we did was feed through raw pixel values, just one by one. We didn't help it generalize. We didn't help it kind of have a different perspective, maybe a little bit. Like, for example, a convolutional neural network, which is going to kind of take chunks of pixels at a time. Well, it might go down to a raw pixel, but it's like a raw pixel. Then maybe chunks of pixels and stuff like that. And those are the layers. Or even, you might just not even have layers, but it's just like a chunk, and then it slides down a chunk and slides down a chunk. Anyway, that means nothing to you. That's fine. But that has a little bit more of a logical approach to it, whereas here, we're just like throwing data at the neural network, and we're just like, yeah, figure it out. And the neural network figured it out. And while 95% isn't like industry standard for that exact specific task, the point is we threw a pretty challenging task at the machine, just gave it the most basic form of data possible, and it still came up with a pretty darn good model. Like, I think that's just amazing, right? The accuracy could be better with a better model and a convolutional neural network maybe and some more work, but honestly, that's a really good score for what we like, the effort that we put into it. And I think that all that does is, while not being the greatest score, it does kind of show you the incredible value of a neural network, or a deep neural network anyway, at just coming up with models. Like, that's pretty cool. Anyway, I think that's cool. So, not without errors, but I'll probably leave them in there just simply because it seems like people don't really mind when I leave the errors in, and I think it actually helps because, working in this code is like confusing as it is, and I've probably done too much of this today, but working in the code is just confusing. You're going to make mistakes, and you're going to get a bunch of big errors as you play around with this. Like, that's going to be really common. So I'm going to leave them in there. You probably get used to these errors, and those big C errors, like Python plus C errors. Those are kind of annoying to work through. But at the end of the day, the biggest thing that you need to look for is the stuff that like I'm seeing line 728. I'm like, I didn't write 728 lines. So I'm just like scrolling through looking for my code, right? And I was still able to find my code and figure out what the problem was. Because like some of this stuff is talking about vector shapes and all this, and clearly it's getting an empty shape somewhere. And that probably would have been a useful-ish. But that didn't tell me enough. I just knew it was empty, but I didn't know, what vector is empty and stuff. So find where in your line of code and your code it messed up. So anyway, maybe more errors to come in the future videos. But regardless, we got 95%. We only did 10 epochs, and it really didn't take that long. So other things you can immediately do is you can just add more layers. You can make the layers more complex. That may or may not help. It might actually decrease your accuracies. And many times, basically, the simplest form possible is usually the best. That's a good rule to go by. But obviously, it's like a super simple, some things won't work. But the simplest you can get away with is pretty much always going to be the best. But anyway, that's all I have for now. If you're getting any errors, feel free to post them below, and I'll do my best to kind of help you out if possible. In the coming tutorials, the MNIST dataset is really cool and all, but I think the next step that needs to be taken is working with your own data, acquiring your own data. So we're going to get some data from somewhere. I haven't totally decided where I want to do it or what kind of project I want to work on. So if you're watching this tutorial and it's fairly recent, feel free to comment below, give me some suggestions or requests on what you want to do. I do have some ideas. I kind of want to work with I'm not even going to say. I don't want to ruin it in case that's exactly what I do. But anyways, if you have suggestions or something, leave them below. We'll probably have other projects too. I think the whole neural network thing is fascinating enough to warrant maybe multiple projects in it. So anyways, questions, comments, leave them below. In the future, we'll work on kind of our own thing, basically with this simple neural network. And then as time goes on, I'll probably add some more with convolutional neural networks and some of the other models as well. So if you have questions, comments, concerns, whatever, leave them below. Otherwise, thanks for watching, and until next time.